Hi everyone. Today this is the third lesson. Not a lesson exactly, but a walkthrough through a great theorem from my perspective. I like it because it's, from my perspective again, it's the most fundamental one for all of the deep learning because as I know it so far, the most of it is built with the usage of neural networks. Some are with, to be honest, little additions like CNNs when the neural network is not really dense. By not really dense, I mean that the neural network that we were talking about today, it's dense, and not just today, throughout the two previous videos. What it means that the neural network is dense is that every neuron is, yeah, it shows it great, is that every neuron is linked to every other neuron. So we have output here, we pass it to here, here, and there are different kinds of neural networks. For example, a CNN, which is not dense, and therefore the output of the neuron goes to, for example, those three other neurons, and those neurons are blind to the output of this one. So, but again, all of the modifications are solely created just to make the performance better, because overall, again, with the example of CNNs, we can actually make our neural network understand what is on the image itself. Because as we've learned, and to be honest, I think we've learned the like 99.9% of this paper, of the material of this paper. And as we know, a one-layered dense neural network can mimic every existing function, and so when we see an image, it's actually like a different function which our brain actually uses to like classify an image of a cat that it's actually a cat. So we actually see some patterns, our brain notices some patterns, and we actually notice them. So a neural network can do that because it can actually approximate every existing function in the whole world. So that's it. And today we're gonna jump to the third. It was a little introduction, I'm sorry. Today we're gonna jump into the third part of the paper. Third out of results for other, and third out of 4 because summary. Maybe we're gonna look at it, but it's not actually something worth reading from my perspective because it's just a summary of everything. But maybe we will. Yeah, we'll see. So yeah, let's begin the third stage, the application of artificial neural networks. In this section, we apply the previous results to the case of most interest in neural network theory. So actually, yeah, our results are interesting to neural network theory. A straightforward combination of theorem 1 and lemma 1. Basically, the things that we were talking about that are actually 90% of the whole paper, shows that networks with one internal layer and an arbitrary continuous sigmoidal function can approximate continuous function with arbitrary precision, providing that no constraints are placed on the number of nodes and the size of the weights. So what it basically means, we had a little representation here. I think we're gonna keep it and actually create a little neural network that is not gonna look like it's a formal one. It's gonna have squared nodes, but again, who cares? Let's say we have just one input, and I'm gonna drop a pencil because I don't care about how good it's gonna look. Yeah, we have a certain input. No, let's actually have a dense neural network that has like 2 inputs, because it's gonna be a little bit more interesting, and it's gonna even 3 inputs. It's gonna be more interesting in terms of we're gonna actually show what the weights are. Yeah, let's gonna do something like that. Yeah, So basically yeah, and another node we're gonna add here. So what we basically do is that we have 3 inputs, let's say x1. I'm gonna use indexes instead of x, y, and z because actually y and z are gonna be used for different purposes. At least y is gonna be used for a different purpose. x3, yeah. And by the term of dense, as I was referring to previously. So what is dense actually? We have one input. This input goes to every neuron here. Yeah, I'm gonna try to do it a little bit faster, but I'm not gonna be able to keep up with that. Yeah, it doesn't look great, to be honest, but still, that's the thing. This input also goes to all of the existing neurons. So yeah, something like that is gonna look extremely bad, but I think you will understand what that basically means. And the same thing with this one. Yeah, so yeah, here, 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 and for the last one here. So every neuron currently has x1, x2, oh, I'm sorry, x1, x2, and x3. Yeah, and everyone has them. Just like, let's pretend they have x1, x2, and x3. And what we're doing here, every output, some black box happens here. We're gonna break it down, but because basically we're talking about the weighted sum here, and now we're gonna be talking about the neural networks by themselves. So it's a little representation about what the neural network is, and as well as the representation, it also serves the purpose of linking the theory that we were talking about previously to the theories that we're gonna be talking about right now. So yeah, this output goes here, this output goes here, here again, everything to the last node. Yeah, like that. And let's say this node again has something, let's call it like z, y. It has the output is z, so this gets us z1, this gets us z2, z3, and again and again and again until z with the index of I. So yeah, that's it. We have them all. I'm gonna write it like that. What actually happens here when I say that black box set? As you may know, we have the sigmoid function. I think you probably learned it currently. So yeah, that's it. That's our. Let's actually do something like that. This is actually our sigmoid function. Yeah. And when we say that we apply the sigmoid function to every layer of the neural net, or to every node of the neural net, I'm sorry, what we basically mean? We mean is that obviously we have three inputs, and saying the first thing that you would probably be thinking about is that we have 3 sigmoids, and we apply firstly x1 gets some value, x2 gets some value, and again, and sum them all up. But that's not the case. That doesn't make any sense. It basically means that every input is worth it, but it's actually not. I mean, they all worth something, but we should have weights. And if you watched the previous I think it was the first video, we've touched the idea of the weighted sum. What the weighted sum is, it's something like that. This is the core idea. It's an extremely important thing. And as you probably think, we have actually referred to the weights. Yeah. So yeah, we refer to weights, so weights are like W. And what we're doing here, let's say that this weighted sum of our like 3 inputs is actually Y. I'm sorry, it's actually Y, yeah. So you may guess what happens to the sigmoid currently. It just becomes like that. Oh, by the way, how does it look actually? Ah, it doesn't look anyhow. Alright, whatever. So yeah, this is our sigmoid right now. So they all have different weights, so all of the nonlinearities are different. As they all have different weights, we pass yeah, look, it looks cool. We pass x1, it has different weight, x2 different weight, x3, they may be all the same, but the thing is that weights may be different for all of the nodes. And something happens here, and we pass all of the values here. And this also has its own sigmoid. Again, the same idea, like this output may be more important. So the weight of this node is more than the weight of this one, for example. Again, weighted sum of the outputs of those nodes, applying sigmoid, and we would get a kind of a value. And an interesting thing here is that this value is between 0 and 1 actually. I think I'm gonna use brackets like this, because actually there is only the limit, we never actually reach 0 and 1, but yeah, I think it makes sense. But probably the braces are squared, but now I think they're like rounded. Alright, so we've broke down so far this thing. This is the theorem 2 below. The consequences of that the result of the approximation of decision functions for general decision regions is made afterwards. Decisions is like x more than 1. Like function gives 3 if x more than 1. Alright, we'll see afterwards, as the Sebenga says. Just Sebenga without that. Alright. Okay, just what we have here, the basic. Then finite sums are dense. In other words, there is a sum. Yeah, we've actually proven that before. Yeah, it's actually like, yeah, it's actually not worth, I think, it's even not worth proving, it's just, like, it's extremely important, like, I understand why he has placed it here, but overall, it's like intuitive, and throughout our, like, explanation from the second part, I think, we can basically infer it. So yeah, and in the proof he says that combine theorem 1 and lemma 1, noting that continuous sigmoidal satisfy the conditions of that lemma. Yeah, just as we've stated. Alright, we now demonstrate the implications of these results in the context of decision regions. Let M note, I don't know what that is. Yeah, advanced math hits hard. Yeah, like this one. In measure theory, yeah, what is it in simple terms? Lab is good. Oh, I'm sorry. Mathematical precise way to define the size, length of area, volume of bizarre set of numbers. You could never, like, we want to complicated shape and want to know the total area. Cover that shape with many small rectangles, set up the area. Yeah. If you smaller and smaller, you estimate get better, the less big you measure is the limit of this covering process as the boxes get infinitely small. Alright, they are like extremely small, whatever. It is the smallest possible total area of all the boxes that completely covers all the set. Simple shapes, complex sets. What if you want the volume of all irrational numbers between 0 and... How can I... What's the total length of a fractal? Alright, so this is just a complicated thing related to... I want to show I want to see the formula. There is no possible formula for it. Yeah, that's like... Yeah, that's basically the shape, the area. Hell, I mean the volume, I'm sorry. Because at schools, I think kids are actually told that the volume is, by the definition, the sum of the products of the sum of the squares of length of squares, of little squares that actually that are actually made up into some kind of a figure that we want to find out the... No, in terms of volume is gonna be the power of 3. Like, yeah, I'm sorry. So what I want to say is that just when referring to like to school definitions, volume of a 3D shape is actually the sum of third powered lengths of squares, of little squares that all like make up the figure itself. But alright, let's move on. Let be the partition of into key disjoint measurable subsets. Define the decision function according to... Yeah, basically, bro, he again. That's the only part why I don't like breaking down like papers that I refer as complicated. You might not, but I refer it as a very sophisticated one. But that's the problem, because what he actually says is that alright, we've proven that actually our theorem, again referring to this thing, works for functions that can be represented. Yeah, by the way, I want to see how he was firstly stating the finite sine triangular Borel measures. So again, just a little, I think, clarification that Borel measure probably doesn't. So does Borel measure of finite things include decision functions? I think it does. Yes, and by extension measures encompass the Borel functions, which include the central classes of decision functions. Indicate, yeah. So why do we exactly no, we actually now we demonstrate the implications of these results in the context of decision regions. Like, yeah, no. Yeah, we've actually proven that we're dense because the Borel measure includes the decision functions. What I mean by a decision function, he states it as a very, very complicated whatever he is saying that is. But overall, the decision function is something like that. Overall is actually just like in simple terms. Like that. It may be not even 5, it's like 0. And 1. f x is less or equal than 0. That's it. Oh, I'm sorry. Like that's basically it. So it's a decision function. We have this. I think in mathematics it's not referred as if statement, but I like that representation. So if we have a statement, it's basically the decision function. And I think it's important because we actually work with like I'm sorry. Yeah, we actually work with the real world, and in the real world we basically encounter a lot of like if statements, so-called if statements. So if we had woken up late, I would have been late to school. So this is the if statement. So we actually want we actually want neural networks to be able to represent these ideas, because it's pretty important, and that's the only reason why we're doing that. So those are so-called decision functions. So yeah, and we can classify X accordingly, so it works both ways. The issue is whether such a decision function can be implemented by a network with a single internal layer. We have the following fundamental results. No, we actually have this Whoa. Then we know that the issue is whether a decision function can be implemented by a network with a single internal layer. Alright. Basically, I think we're just dancing with the thing that we were talking about for a long time, but have the following fundamental result. So yeah, probably alright, let's just talk that like Borel measure includes decision functions. So yeah, let's mark it all this way and return to main results. Finite and regular Borel measures. The finite regular Borel measures does the space yeah. Oh well, yeah. Yeah, so that's it. That's it makes actually sense. So we've proven that not for decision functions. That's it. Yeah. Yeah. So we're gonna return to the important thing, like to this thing, and we're gonna and we're gonna work it out. We're gonna comprehend that. Yeah, so we're gonna work on this issue probably. Let sigma be a continuous sigmoidal. Alright, let f be the decision function for any finite measure partition. Alright, of yn. For any error more than 0, there is a finite sum of a form, so that All right. H. Because of continuity, we will have the position of having to make some incorrect decisions. So yeah, wait, what? By this guy's theorem, there is a continuous function h and the set of d with whatever, so that h equals for x equals d. Now h is continuous, and so by theorem 2 we can find a summation of the form g above to satisfy for. Then for d we have this thing. Because of continuity, we are always in the position of having to make some incorrect decisions about some points. This result states that the total measure of the incorrectly classified points can may be arbitrarily small. In light of this, theorem 2 appears to be the strongest possible result of its kind. We can develop this approximation idea a bit more, considering the decision problem for a single clause. Yeah, then, alright, otherwise f is the indicator function. Yeah, this is cool. This is easy, and I think this is the excuse, because what we're saying, probably you actually noted that negative x. You actually noted that this thing looks like can we actually do like 1f x like more than 5? No, we cannot do that. Does it include such things? Entrance expression, no, we don't have. So have you noticed it? By this we have 1, after some value we have 0. So there is even a theorem by this guy, is that the thing is that we can actually just say that there is another function that belongs to our like Borel measure of regular finite Borel space of regular Borel measures whatever, that can mimic this function, this decision function, so it all works out. Cool. Alright. We can. How many theorems have we left? No, yeah, alright, this is cool. Theorem 2 appears to be the strongest possible result of its kind. We can develop this approximation idea a bit more by considering the decision problem for a single closed set D belongs to. Yeah, we can develop this approximation idea a bit more by considering the decision problem for a single closed set, then f equals 1 if xd and f equals 0, otherwise f is the indicator function of the set. Okay, suppose we wish to find a summation of the form 1 to appropriate the decision function let so that is a continuous function. Now we set the maximum so that for points farther off, then moreover x is continuous. Guesses, while guesses the decision procedure is correct, distance at least away from D if it's within the distance. Classification depends on the particular choice. This observation like we want to approximate a function that gives 1 if x belongs to some like space, and 0 otherwise. We're saying that we're finding the minimum value. Now we set, yeah. Yeah, so we're finding the minimum value of whatever. And then we're restating the f function. Yeah, f equals 0 from, yeah, alright, it's continuous. Like, you get that we just replicate the f. So just to give the basic idea, right? So, firstly, and more importantly, we've actually proven the thing about the decision function. So the second one is just the representation of it. And with the representation, what we need to do is that we want to develop just an understanding of it. So what we have the function f that does something. And what we're doing is that we're restating the f, so we can actually write it in a way that it's a continuous function. And if it's a continuous function, that we can actually recreate it using our neural network. Yeah, the problem is that I don't understand what the y is. Yeah, I think we can actually do something interesting. We can just... No, I think it's not gonna work. Whatever. Yeah, so the basic idea is that... Yeah, so... Probably we're finding the minimum value of like... I don't know. Okay. Yeah. So the basic idea is that I think we may not last long on it. So yeah, probably like the basic idea is that I don't actually understand what y is in these terms. And probably I'm not gonna think for another like 20 minutes of the video time. I'm gonna just refresh it. I'm gonna try to refresh it. After probably I'm gonna mention about it in the next video, like tomorrow. So what we did today is that we've actually found a big gap for neural networks in our theorem, is that the whatever space of Borel measures, it's called something like that, does not include decision functions. So we cannot make decisions basically with our neural network so far. So what we did, we've actually proven that by some guy with whose name starts with L, that decision functions are nothing more special than just regular functions that are included in our space. And we've actually proven that our neural network can actually make decisions. So yeah, I think that's it. Yeah, so I think the whole idea is actually pretty intuitive, but still it works, so why would we bother? And I think that's everything. So thanks for listening. In the next video, we're gonna end up this paper by looking on the results for other activation functions. But so far, I can guess that, based on my experience, there are obviously other activation functions that work, and they also have the property of being discriminatory. So they also break the space into two halves. And we're gonna general sigmoidal functions. We are probably saying that so yeah, we're probably talking about different functions, and we're gonna briefly look at the summary, but I don't think we're gonna spend a lot of time on it. So yeah, that's everything. Thank you for listening, and bye.